We are going to look at one more recurrence that we will solve using change of variables. Suppose t of n is given to be the square root of n times t of the square root of n plus n. Once again, the original problem of size n is expressed in terms of problems of size the square root of n. So this gives us a hint that we need to proceed by letting n be equal to 2 to the power m for some m, because by doing this we can express the right hand side as 2 to the power m by 2 times t of 2 to the power m by 2 plus 2 to the power m. So if n is 2 to the power m, the square root of n, which is n to the power half, will be 2 to the power m, and the whole thing raised to the power half, which would be 2 to the power m by 2. So we have changed this recurrence into this recurrence. And as before, we will let s of m be equal to t of 2 to the power m. This means the right hand side will become 2 to the power m by 2 multiplied by s of m by 2 plus 2 to the power m. So we are letting s of m be equal to t of 2 to the power m. So s of m by 2 will be t of 2 to the power m by 2, which is why we replaced t of 2 to the power m by 2 by s of m by 2. Now, can we solve this recurrence? Well, it's not something that we can solve using master method, because 2 to the power m by 2 is not a constant. It is a function of m itself. So this is not a recurrence of the form s of m equals a times s of m by b plus f of m. That's not the form of this recurrence. So we need to use some other way of solving this recurrence. One way of approaching this is to simply open up this term s of m by 2 and open up the resulting terms of s recursively and see what happens. So to do that, let me first express s of m in a slightly reordered way. Let's first write 2 to the power m, and then we'll have the first term over here written later. And the reason for writing it in this way is that we can go on expanding this term s of m by 2. If s of m is this, s of m by 2 is going to be, you can replace m by m by 2 throughout, and we'll get s of m by 2 is 2 to the power m by 4 multiplied by s of m by 4 plus 2 to the power m by 2. And again we'll write this as 2 to the power m by 2 plus 2 to the power m by 4 times s of m by 4, so that when we replace s of m by 2 over here, with the right hand side over here, we'll get this s of m by 4 at the very end. So we are basically taking this s term at the very end and going on expanding it for smaller and smaller sub-problems. So we can write this as 2 to the power m plus 2 to the power m by 2 multiplied by 2 to the power m by 2 plus 2 to the power m by 4 times s of m by 4. This will become 2 to the power m plus, when we multiply these two terms, we'll get 2 to the power m. And when we multiply this term with this term, we'll get 2 to the power m by 2 plus m by 4 times s of m by 4. Let's expand s of m by 4. We are basically going to search for a pattern. You'll see that a pattern emerges as we go on expanding this s term successively. So let's do this one more time to see what kind of pattern we get. To get the expression for s of m by 4, we need to replace m by 4 throughout. So this will be 2 to the power m by 8 multiplied by s of m by 8 plus 2 to the power m by 4. So substituting the right hand side over here, we get 2 to the power m plus 2 to the power m plus 2 to the power m by 2 plus m by 4 multiplied by this right hand side. And again we'll write this term first, and then the second term will be 2 to the power m by 8 multiplied by s of m by 8. So this becomes 2 to the power m plus 2 to the power m plus 2 to the power m by 2 plus m by 4 plus m by 4. The sum of these three terms is m. The other term will be 2 to the power m by 2 plus m by 4 plus m by 8 multiplied by s of m by 8. So we can see a pattern emerging over here. We have terms of the form 2 to the power m at the beginning. Every time we open up this s term, we get one additional 2 to the power m as a result. And in addition to this, we have this term at the end, which has 2 raised to the power m by 2 plus m by 4 plus m by 8. And this will continue on. So when we open s of m by 8, we'll get a fourth power over here, which will be m by 16. And that will be multiplied by s of m by 16. You can see that over here. If we let's quickly write down what s of m by 8 will be. S of m by 8 will be 2 to the power m by 16 times s of m by 16 plus 2 to the power m by 8. So again, if we replace s of m by 8 with this right hand side over here, this 2 to the power m by 8, when it's multiplied with 2 to the power m by 2 plus m by 4 plus m by 8 will yield 2 to the power m. So that will add one more 2 to the power m term to this list of terms over here. And the other term will be 2 to the power m by 16 times s of m by 16, the whole thing multiplied by 2 to the power m by 2 plus m by 4 plus m by 8. So in the next step, this will become 2 to the power m plus 2 to the power m plus 2 to the power m plus one more 2 to the power m, and the other term will be 2 to the power m by 2 plus m by 4 plus m by 8 plus m by 16 times s of m by 16. So we can write down what the right hand side will look like after I steps. So after I steps of opening up the recursion for S, we'll get I instances of 2 to the power m plus, as you can see here, we have 4 instances of 2 to the power m when we open up S of m 4 times. This is the first time we opened it. This was the second time we opened it. This was the third time we opened it. And this was the fourth time we opened it. Every time we open up S of m, we get a problem of half the size multiplied with some function of m, of course. But this S term has its argument reducing by a factor of 2 every time we open it up. So after 4 steps of opening up, after 1 step of opening up, we get S of m by 2. After 2 steps of opening up, we get S of m by 2 squared. After 3 steps of opening up, we get S of m by 2 cube. And after 4 steps of opening up, we get S of m by 2 to the power 4. And we get 4 instances of 2 to the power m. So when we open this recursion I times, we would get I instances of 2 to the power m. We would of course get S of m by 2 to the power I over here in the last expression, and we'll have a power of 2 which will be a continuation of this pattern, m by 2 plus m by 2 squared plus m by 2 cube plus m by 2 to the power 4 and so on. M by 2 plus m by 4 plus m by, let me write this as 2 squared, m by 8 is m by 2 cube, m by 16 is m by 2 to the power 4 and so on till m by 2 to the power I. And this is multiplied with this power of 2 to the power, this expression is multiplied by S of m by 2 to the power I. Now we can continue doing this until we end up with a problem of size 1, at which point we terminate. So suppose that after h steps we get S of 1 at the in the right hand side as part of the right hand side. So this term reduces to s of 1. This means that m by 2 to the power h must be equal to 1, because after h steps we would have h instances of 2 to the power m, plus we would have some power of 2, where the power is given by a summation from m by 2 up to m by 2 to the power h. And this would be s of m by 2 to the power h. And we are saying that after h steps we get a problem of size 1. So m by 2 to the power h can be equated to 1, which means h is log of m to the base 2. So we can write s of m then as h times 2 to the power m, because there would be h instances of 2 to the power m, plus s of 1 would be just some constant. S of 1 would actually be t of 2 to the power 1, which would be t of 2, and t of 2 is going to be some constant. So s of 1 will also be some constant. And this will be multiplied with 2 to the power m by 2 plus m by 2 squared plus m by 2 cubed, and so on till m by 2 to the power h. Now this term, this first term, is 2 to the power m multiplied by log of m, because h is log of m. The second term is some constant multiplied by this power of 2. Now, since we are interested in the asymptotic complexity of s of m, we don't need to exactly calculate what this summation will be. At least not if it turns out that this term is the dominant term. If we can argue that this term is going to dominate over this term, then we don't need to exactly calculate what the value of this summation will be. We can simply drop this term as a lower order term. Now, what if this series had continued till infinity, till for an infinite number of terms? So instead of terminating at m by 2 to the power h, let's say it had gone on till infinity. In that case, we would have got something larger than this finite series. Now, this is a geometric progression or geometric series. M by 2 is the first term, and the common ratio is half. So had this been an infinite geometric series with a common ratio less than 1, this summation in that case would have been the first term divided by 1 minus the common ratio, which would be m, because 1 minus half is half. M divided by 2 divided by 1 divided by 2 is just m. So if this had been an infinite series, we would have obtained a power of m. But because this series is being cut off at m by 2 to the power h, the power of 2 that we are going to get here will be less than m, will be less than what we would have got if this series had continued indefinitely. So we can argue that the power of 2 is going to be some number less than m. So it's going to, we can write it as 2 to the power m minus epsilon, where epsilon is greater than 0. It's some positive constant. Now the first term has 2 to the power m, in fact multiplied with another term log of m. The second term has just a constant multiplied with a power of 2 that's less than m. So we can see that this is a lower order term. This is the dominant term. So what we can do is we can drop the lower order term and say that s of m is going to be theta of 2 to the power m times log m. This means that t of 2 to the power m is theta of 2 to the power m times log of m. And t of 2 to the power m is nothing but t of n. If you recall, we let s of m be t of 2 to the power m, and before that we had let n be equal to 2 to the power m. So s of m is really t of 2 to the power m, which is really t of n. So again, changing our variables back to n, we get t of n on the left hand side equals theta of, if n is equal to 2 to the power m, we can write n in place of 2 to the power m over here. And we need to express log m also in terms of n. So if n was 2 to the power m, what would be log of m? Well, let's take log of both sides. We would have got log of n equals m, taking log of both sides here, log base 2. But we need to express log of m in terms of n. So to get log of m in terms of n, we need to take log base 2 of both sides again. So we get log of n equals log of m. So if you want to express log of m in terms of n, we'll need to substitute it with log of n. So this log of m can be replaced by log of n. So we get the solution to the original recurrence. T of n is theta of n times log of n. Again, we did this via change of variables, noticing that we have a square root of n on the right hand side. So we have seen 3 examples where the same approach pretty much worked. We let n be equal to 2 to the power m, and we create this new function s of m and a simpler recurrence relative to the one that's originally given to us. And we can solve this simpler recurrence. In this case, we couldn't solve it using master method, but we could solve it by just opening up this recurrence, this s term successively to get a summation. And again, a pattern emerged, just as we used to see a pattern emerging in the recursion tree method, where we would pretty much do the same thing, opening up the function s or t in that case successively for smaller and smaller subproblems. And of course, instead of depicting the overall summation in a single line like the way we've done here, we used to depict it diagrammatically in the form of a recursion tree there. But here we've just depicted it in a single line. But we are effectively doing what we were doing in the recursion tree method, except that we are doing it in a non-diagrammatic way. But as in the recursion tree method, we noticed a pattern emerging once we opened up the S term 3 or 4 times. And then we extrapolated the pattern to H steps so that we end up with a subproblem of size 1, which is where we terminate this process of opening up the function S, because we end up with a subproblem of size 1. And at that stage, we computed what the asymptotic complexity of this summation would be. We saw that one of the terms, which is the more complicated term among the two, turns out to be a lower order term. And so we were able to ignore it, and having obtained the asymptotic complexity of S of m, we go back and express S of m in terms of n. So that would just be T of n, and m can be expressed in terms of n on the right hand side. And that's how we obtained the solution to this.